We've been talking about real numbers and how they can be represented. Let's talk a bit about irrational numbers and the most common class of irrational numbers that we see, that being surds. So this is really just a recap, I guess, of how we deal with surds. It's basically an irrational number, any number that includes a radical symbol and can't be simplified. So for instance, the square root of 4 is not an irrational number because we can work that one out, we can simplify it. It doesn't have to be a square root. Cube root of 2 would be an irrational number as well. So anything with a radical sign. So our rules for simplifying surds, this one allows us to do it because we're trying to make one of our factors a perfect square, and then we can find the square root of that. Division, I guess that's just saying, look, it doesn't matter what order you do the division first. You could find the surds, then do the division, or do the division first, it doesn't matter. And I mean, it's obvious, I suppose, but the square root of a squared is equal to a. Well, that's sort of true. It's sort of true. If the square root of a squared is equal to a, as long as it satisfies one condition, what would that condition be? Yeah, exactly. So as long as a is greater than or equal to 0, that would hold true. So root 50, we're looking for a perfect square. 25 obviously is the biggest one that goes into that one. Now, of course, you don't write that line down, that's what you're thinking. Okay, so, oh yeah, that's 5 root 2. We saw back in algebra, you remember. Okay, x squared, we could write it as. But remember, a quicker way of doing those ones is to think of it as an improper fraction. So 3 on 2 would be 1 and a half, and you can get that. 5 on 4, well, I can't work out the square root of 5, but I can work out the square root of 4, so root 5 on 2. Root 20 on 9, I can work out root 9. Root 20 I can simplify, so we get 2 root 5 on 3. So all those sorts of ideas, I guess we're talking about. So surd arithmetic, and you'll notice it's exactly the same wording as the very first words that I wrote down way back day one. Difference is, instead of using the word terms, I've used the word surds. And the reason for that is a surd is unknown. And in algebra, you're dealing with unknown. So all those algebra rules apply in surds, because a surd is just another unknown. It's just like saying, well, root 2 is the pronumeral, if you like, that represents whatever the square root of 2 is. We just don't know what it is. So we get something like this. Well, I can't add the 4 root 3 and the 6 root 2 because I don't know what those things are. They're different surds. But if I've got 4 lots of root 3 and I take away 1 lot of root 3, I do know that's going to be 3 lots of whatever root 3 is, plus 8 lots of whatever root 2 is. So we end up with binomial products, just like we did in algebra. And in this case, nothing tidies up. Very common sort of question we see with surds. Root 2 plus 1, root 2 minus 1. Whoop. They're what we call conjugate surds. Conjugate surds. So we get 2 minus 1, which is of course 1. A perfect square. So same idea. Square. So first one squared minus twice the product. Second one squared. In this case, of course, the 4 and the 2 can tidy up. 6 minus 4 root 2. So anyway. So that's just we shall do that.